In modern security operations centers, analysts face a persistent and costly challenge, turning high-level security intentions into actual deployable network policies. This process, often referred to as policy refinement, is critical for protecting organizational assets. Yet in practice, it remains largely manual, error-prone, and deeply constrained by the complexity of real-world networks. Why? Because security intent, like block malicious traffic from compromised hosts, is abstract. It doesn't tell you where to enforce it, how to enforce it, or which devices can even support the required controls. Networks are heterogeneous. Firewalls, web application firewalls, routers, and virtual appliances each have different capabilities. Traffic paths vary, and new threats emerge daily, demanding rapid updates. This gap between intent and enforcement is not just inefficient, it's dangerous. Misconfigurations are a leading cause of breaches. According to industry studies, over 50% of firewall-related incidents stem from human error in policy management. And when networks evolve, new segments added, routes changed, devices replaced, the risk compounds. Enter RefinementEngine, a fully automated system that bridges this chasm. It takes a high-level security intent, a network topology, and real-time cyber threat intelligence, CTI reports, and returns a set of device-specific deployment-ready rules, all while respecting reachability constraints and device capabilities. Let's break down how it works. The pipeline begins with threat intelligence. CTI reports, often written in natural language, describe malware behavior, IP addresses, domains, or attack patterns. RefinementEngine uses an AI-powered module to extract these security-relevant entities, known as indicators of compromise, EOCs. But here's the catch. Raw LLMs can be unreliable in security contexts. They may hallucinate, miss nuances, or produce inconsistent outputs. To solve this, RefinementEngine embeds the LLM's output into CLIPS, a rule-based expert system environment. CLIPS enforces strict syntax, only allowing actions and data structures that are safe, interpretable, and auditable. This creates a hybrid neurosymbolic architecture, AI for extraction, symbolic logic for reasoning. Once extracted, the EOCs, say a malicious IP address or a suspicious domain, are converted into structured facts and templates within CLIPS. These become the foundation for the next phase. Now comes the refiner, the brain of the system. It receives the high-level security intent, expressed in a high-level security policy language, HSPL, and the network model, represented in TOSCA, a standardized language for describing network topologies and relationships. For example, an intent might be, endpoint A is not authorized to access endpoint B. The refiner uses CLIPS to analyze the network, compute all possible traffic paths between the two endpoints, and identify which devices lie on those paths. But it doesn't stop there. It checks whether each device can actually enforce the policy. This is where the Security Capability Model, SCM, comes in. The SCM abstracts what a device can do, its supported conditions, e.g. source IP HTTP header, actions e.g. drop, log, and events, into a vendor-neutral format. So if a firewall supports IP-based filtering but not domain-based inspection, the refiner knows it can't enforce a rule based on a hostname. It only considers devices with the necessary capabilities. Then comes the optimization, minimal enforcement set selection. The refiner finds the smallest number of devices that can block traffic across all paths. It leverages shared subpaths, like a single firewall that sits on multiple routes, so you don't end up duplicating rules. If no such set exists, the system flags the intent as unenforceable, preventing blind deployment. This decision is deterministic, traceable, and reproducible, critical in regulated environments. The output. Intermediate artifacts. For each selected device, a list of required security capabilities, their parameters, and the target control, e.g., iptables, ModSecurity. These artifacts are passed to the converter, which generates a medium-level security policy, MSPL, file for each device. MSPL is a structured, XML-based language that captures policy intent in a way that's compatible with the device's control model. The converter normalizes values, turning IP ranges into canonical forms, for instance, and ensures all required fields are present. Finally, the translator takes the MSPL policy and converts it into low-level, native configuration commands. For iptables, this means generating iptables A forward S80 71 15896D 1721903J drop. For ModSecurity, it produces rules like secrule request headers, host at rx /3 utilities /com $, deny ID 1. This translation is fully model-driven, grounded in the SCM. No heuristics. No randomness. Given the same input, it always produces the same output. Now let's see it in action. In one real-world test, RefinementEngine processed a CTI report about CoinMiner, a malware known to communicate from the IP address 807115.896. The network had 3 paths between the compromised host and a target server. The refiner identified 2 enforcement points, Firewall 1 and Firewall 3. It generated iptables rules for both, ensuring traffic was dropped in both directions. Before deployment, ICMP requests from the attacker IP were fully allowed. After applying the generated rules, every packet was dropped. No replies, no connection. Traffic analysis confirmed the rules were applied correctly, and no manual tuning was needed. In a second scenario, the threat was domain-based. NanoCore malware used the domain hadleshope 3 utilities, com. This was new. No prior knowledge of domain-level EOCS existed in the system. But thanks to Clip's adaptive structure, the system learned how to handle this new type. It dynamically updated its templates to include a URL slot. The extractor parsed the report. The refiner identified that only the web application firewall, WAF, could inspect HTTP headers, and the translator generated a ModSecurity rule that blocked the malicious domain while allowing legitimate traffic. Traffic logs showed identical TCP flows, same source, same destination, but only the malicious domain was rejected. The WAF enforced the rule at the application layer, where only it could see the host header. This is the power of RefinementEngine. It doesn't just react to known threats. It adapts to new types of indicators, payload patterns, new ports, encrypted channels, without breaking the pipeline. And it does so with minimal human intervention. No expert writing rules by hand. No risk of misconfiguration. No delays from fragmented workflows. This isn't just automation. It's autonomous policy engineering. Existing systems tackle parts of this problem. Some focus on policy verification, others on SDN orchestration or CTI extraction. But none unify all stages: intent refinement, topology-aware allocation, capability-aware translation, into a single deterministic deployable pipeline. RefinementEngine closes that gap. It's not a tool for one-off tasks. It's a continuous enforcement engine that evolves with the threat landscape. Future work will expand its scope, supporting more policy types, like segmentation, DDoS mitigation, or encryption enforcement, and deepening integration between the AI extraction module and the symbolic translation engine. But for now, the message is clear. Security policy refinement doesn't have to be manual, slow, or error-prone. With the right architecture, combining symbolic reasoning, model-driven translation, and adaptive AI, organizations can transform threat intelligence into real-time, correct, and deployable defenses. The future of network security isn't just smarter tools. It's smarter automation. And RefinementEngine is leading the way.